Today we're going to discuss about the partial derivatives of functions of several variables. Right. So, what do we currently know about a function? We have seen functions of the form, say y equal to some f of x, where x is said to be the independent variable and y being the dependent variable. Right. So far we were actually discussing about the case where we have only one independent variable and only one dependent variable. But this may not be the situation always. There can be more than one independent variable and there can be more than one dependent variable. Right. Especially in the physical applications or applications of mathematics in other fields of science, we usually encounter the functions with more than 2 or 3 independent variables and several dependent variables. Right. So now we are going to discuss about such functions where we have more than one independent variables. For now, we are not discussing anything about the functions with more than one dependent variable, but let's consider certain functions with more than one independent variables. Right. So, consider a function of the form z equal to f of xy. See, here we have two independent variables and a single dependent variable z. So this function is a function of two variables. Right, we have two independent variables here. So we call this function to be a function of two variables. And this is actually a rule assigning xy to the value f of xy or z. Right. So this function assigns a value, a z value, for every pair xy. This function assigns a value z for every function, every pair xy. Right. Such a setup is called a function of two variables. See, there can be functions of 3 or 4 or any number of variables. We'll see some of them in the due course. So for now, let's consider a function of two variable. Say z equal to f of xy. So you know we have two independent variables and one dependent variable. And the next is about the graph. Right. Consider the earlier case where we had functions of the form y equal to f of x. Only one dependent variable, independent variable and one dependent variable. In that case, we had our graphs drawn on a plane. Right. One axis is dedicated for the independent variable, usually the x-axis, and the other one is dedicated for the dependent variable, usually the y-axis. Right. This was how we had our graphs drawn on a plane. But see, can we represent this pair on a single axis? We cannot, since ordered pairs are actually coming from the plane. Right, they are from the plane. The points in the plane are actually denoted with ordered pairs. So, instead of having a two-dimensional setup like a plane, to draw the graph of a two-variable function, we first need a plane. We need a plane, say xy plane. Xy plane, simply to denote the independent variables or the domain. You know what is the domain and range of a function. I hope you remember. If we have a single variable function like y equal to f of x, the set from where x's are coming is called domain. The set from which x takes values is called domain, and the set of all y's corresponding to each of these x's from the domain is called the range. So these both are sets. This is the set from which x takes values, and range is the set in which contains all the values of y's for each x in domain. Right. Okay. So we need a plane itself to designate the domain xy or the pairs xy of the function z equal to f of xy. So where does this z can be marked out? So we introduce a new axis. I have a limitation to draw it on the board. Suppose that axis comes out of the plane of the board. That axis comes out like this. Right, it comes out and goes inside. So for the sake of completeness, I just draw it down. Suppose this goes inside. Right. So this is the z-axis for now. Okay, so now we got a three-dimensional setup or a space. A three-dimensional space, and in this space we draw down the graphs of two variable functions. Right. So to draw the graph of a function with two independent variables and a single dependent variable, we need a three-dimensional setup. Okay. So remember that. That's about the graph. And now another important concept about this is the level curve. See, the graph of these two variable functions usually happens to be surfaces. Okay, so what are level curves for now? Suppose we have a function z equal to f of x, y. For instance, I fix z is equal to a constant, say c. I fix z equal to a constant. Using that value of z, I can rewrite this function as f of xy equal to c. Right. If you try to draw down the graph of this function, you will get a curve. You know what is a curve? We have been discussing about curves so far. So, if you try to draw down this graph, f of xy equal to c, you will end up at a curve, and that curve is called the level curve f of xy equal to c. Remember, if I change this c to some c2, the level curve will change. Okay, so the level curve is actually depending totally on the constant. Right. So, level curve is obtained by simply assigning a constant value to the z. Okay, let's see an example now. Things will be much more clear when we go to example. So consider z equal to f of xy or let xy f of xy equal to y square minus x square. See, this is a function of two variables. We have two independent variables, and z is actually depending on both y and x. Okay, so we have two independent variables and one dependent variable. Now, the level curves are obtained by simply assigning the value c. So, y square minus x square equal to c gives the level curves. So, if I choose c equal to 2, the level curve is y square minus x square equal to 2. If I choose c equal to 0, y square minus x square is equal to 0. Right. These are all possible level curves. There are infinitely many level curves for this graph or for this function. You can choose different values for c and obtain different level curves. Okay, so this is how we use or we deduce the level curves from a function. Okay. So can there be functions of more than two variables? Definitely yes. So there can be functions of the form z equal to or z, we can use z here. So w equal to x, y, z. There can be functions of the form w equal to x, y, z. As like in the case of two variable functions, We can think about the level curves of three variable functions as well, and can be obtained by simply assigning constant values to w as f of x, y, z equal to c. Suppose we have a function w equal to say x square plus y square by z. Maybe z not equal to 0 for this case. So if it is the case, you can simply obtain the level curves by simply substituting w equal to a constant value. Okay, so this is just a heuristic example. You need not depend much on this. Right. Now we move to the crux of the session, the partial derivatives. The partial derivatives. Let's start with the function of single variable where we define derivatives and we try differentiation. Suppose we have a function y equal to f of x. We define the derivative y dash as the rate of change of y with respect to a change in x. Right? We defined y equal f of x as a function and y dash as the rate of change of y with respect to a small change in x. How did we explain that, or what was the expression to find the derivative? The definition was say we had a definition with limits, something like limit delta x goes to 0, f of x plus delta x minus f of x divided by delta x. This was actually the expression for first derivative f dash x of f or y dash, whatever. So this was how we defined the derivative for a single variable function, and the derivative was actually the rate of change of y. See, y is depending on x, so if x changes, y will change. So y dash or f dash was actually measuring the rate of change of y with respect to a small change in x. Now let's excite this to the case of two variable functions. Consider we have a two variable function, say z equal to f of x, y. Right. If this is the case, x and y are independent variables and z is a dependent variable. So z depends on x and y. So if x changes, z will change. Similarly, if y had a change, there will be a change in z as well. So we can think about two possible rates of change here. The rate of change of z with respect to a change in x and the rate of change of y with respect to, the rate of change of z with respect to a change in y. So unlike in the function of single variable where we had a single derivative, we will have two derivatives here to designate or to express the two rates of changes. Okay. They are called the partial derivatives. The partial derivatives. So the partial derivative, see, the rate of change of z with respect to x will be called the partial derivative with respect to x, and the rate of change of z with respect to y will be called the partial derivative with respect to y. Now let's formally define these partial derivatives, and then we can think about the practical applications and the techniques used to evaluate the partial derivatives. So suppose we have a function, two variable function z equal to f of x, y. Right. If it is the case, the partial derivative of z with respect to zx denoted as dou z by dou x, like we used dx, dz by dx for ordinary derivative, we designate the partial derivative as dou z by dou x, is defined as, again, as a limit delta x goes to 0, f of x plus delta x, comma y, minus f of xy divided by delta x. See, we wanted to analyze the rate of change of z with respect to a change in x. So we had a small increment in x. We kept y as it is. We didn't even make any changes into the y part of the function. We had our increment to the x part. Right. So this actually gives us the partial derivative of z or partial derivative of f with respect to x. Similarly, we can give the expression for partial derivative with respect to y. Dou z by dou y equal to limit, say, delta y goes to 0. F of, we are not going to make any change to the x part, and we will make changes to the y part, minus f of xy divided by delta y. Right. So these are the formal definitions of partial derivatives. This gives the partial derivative with respect to y, and this gives the partial derivative with respect to z for with respect to x for z equal to f of xy. Okay, but practically we will not be using these expressions to calculate or to evaluate the partial derivatives. What we do to evaluate the partial derivatives in a practical sense is much more simple. To find, remember this is very much important, to find dou z by dou x or partial derivative with respect to x, simply differentiate with respect to x, keeping y as a constant. So treat y as a constant and differentiate the expression with respect to x. That will give the partial derivative dou z by dou x. So simply to find, similarly to find dou z by dou y, you can simply differentiate the whole expression with respect to y, keeping x as a constant. So this is the most important part of the session. This is how we calculate or we find the partial derivative of a function. We will not use the limit expression anymore. We will simply differentiate with respect to the variable with which we need to find the derivative, keeping all other variables constants. Okay, let's see an example. Consider a function z equal to 4x cube y square minus 4x square plus y raised to 6 plus 1. Find dou z by dou x and dou z by dou y. So let's first find dou z by dou x. So see, how did we explain about dou z by dou x? To find dou z by dou x, we need to just simply differentiate with respect to x, keeping y as a constant. Right, let's do that. So this is a polynomial-like structure, so we can simply differentiate term-wise. So what is the derivative of first term with respect to x, keeping y as a constant? So if y is constant, y square is constant. So 4y square is a constant. 4y square into x cube will have the derivative 3x square. Right, we are differentiating with respect to x square. So 4 into 3 will be 12. 12x square y square. So this will be 12x square y square minus 4x square with respect to x will have the derivative 8x plus, if y is a constant, y raised to 6 is a constant, and the derivative of a constant with respect to x is 0, and plus 1 is again 0. So dou z by dou x is 12x square y square minus 8x. Similarly, dou z by dou y. Let's try to differentiate this expression with respect to y, keeping x as a constant. As we have done earlier, x is a constant, then x cube is a constant, so 4x cube is a constant, and y square will have the derivative 2y, so 4x cube into 2y will be 8x cube y minus, if x is a constant, x square and 4x squares are constants, So with respect to y, the derivative will be 0, and with respect to y raised to 6 will have the derivative 6 y raised to 5, and 1 is again a constant which is having a derivative 0. So this is dou z by dou y, and this is dou z by dou x. This is how we find the partial derivatives with respect to x and with respect to y. Okay. And this is not the only way to denote the partial derivative. This may be also denoted as if z equal to f of xy. Let's clear this off first. If z is equal to f of xy is a function of two variables, the partial derivative with respect to x or dou z by dou x may also be denoted as fx or sometimes zx. Right. These are all denoting the same quantity, the partial derivative with respect to x. Similarly, the partial derivative with respect to y may be denoted as fy or zy. Right. So don't get confused if you find these symbols in your textbook or somewhere.